obviously today we're going to be talking about practical quantum computing. I really wanted to focus on the practical side of things because quantum computing gets a lot of hype in the news, and it's really hard to tell what's real, what isn't. So, I'm going to start off with just kind of looking at some of these news stories. These are just some news stories that I found. I just literally typed in quantum computing into Google News, and these are all things that came up. Quantum computing is a potential cure for cancer. It's going to change the way the world uses energy. It's going to turbocharge healthcare. Quantum computing is going to beat climate change. It's going to be the smartphone of the 2020s. It's going to, it's set to impact the finance industry. There's just so many different claims about quantum computing. And how do we even know which of these are even relevant, which are real? Because it's a very confusing world right now. So before I get into these claims, I really want to talk about the fundamentals of quantum computing. Just like I did in the data science lecture, there's a lot of buzzwords about AI and things like that I clarified ahead of time. In this industry, I really want to clarify a handful of terms because they are misused often. So, first one I want to talk about, superposition. We've all heard of Schrödinger's cat. I think this is a fantastic design for a cat box, by the way. But the principle behind Schrödinger's cat is that if you take a Geiger counter that's measuring the decay of atoms, and that has a 50% chance of triggering a mallet to drop and break some poison that's going to kill the cat, that this cat will, if you completely isolate the system, so there's no way of observing the contents of it, that this cat would be both alive and dead. So, what does that mean to be both alive and dead? And some people point out that Schrödinger invented this to talk about the absurdity of superposition, but it actually shed quite a bit of light on how interesting it is when we really dive into it. So, if we talk about a quantum state, which would be the angular momentum of an electron, or maybe the polarization of a photon, polarization of light. These properties, they could be either linearly polarized or horizontally polarized. They can be spin up, they can be spin down. There's all these number of properties that subatomic particles can have, and what's interesting is that they aren't just one or the other. So if I have a coin and I flip it and I ask you, what is this heads up or heads down? This is a probability distribution. There's a 50% chance it's heads up. There's a 50% chance it's heads down, right? But superpositions are interesting because what I just described to you is something related to knowledge. So when I ask you that question, what is the state of the coin right now? It is one of those things. You just don't know what it is. And that's what we call Bayesian probability. But the thing is, though, is that wave functions, and these quantum properties, they aren't Bayesian. So it's more like the spinning coin. So if I were to ask you right now, is this coin heads up or is it heads down? Is it heads or tails? Well, which is it? It's not really a relevant question. So what we did there was we introduced a logical fallacy of begging the question because we assumed a premise that it could only be one of two possibilities. And the fact is that quantum reality does not abide by Bayesian reality, just like a spinning coin is not a Bayesian problem. The outcome can be Bayesian. The actual state of it right now is not a Bayesian problem because it is not in one of two states. So just like the spinning coin isn't heads and it isn't tails, it could be one or the other after we measure it. If I slam it down and then look at it, it's one or the other. We can reduce it to a Bayesian problem. But when it's spinning, it is not a Bayesian problem. And that's something that's really important about quantum physics that I really want to get across to everyone. And we see this in the famous double slit experiment. Anybody who's ever watched, a physics YouTube video or anything about quantum phenomenon, they always introduce the double slit experiment. And the idea is that, if you were to splash water or something and there was two slits, you would get these cancellation patterns in the background. But you would think that if you just shot marbles, solid objects at these, you would get two lines like this. But the reality is that when you shoot individual photons, they actually land in these patterns. But if you add a photoelectric detector to try to determine which path it went through, it actually shows up as the two bands. And what's going on is when you, in this scenario, when we're not using a photodetector, the light goes through as if it's still in that spinning coin state. It's not yet reduced to a Bayesian problem. It's not yet reduced until it hits over here. But if we add detectors to try to figure out where it is at any given time, we perform a measurement, and then it's a Bayesian problem. It is then one or the other. And so then it will behave as one particle. So just by adding detectors, we change the outcome, because a measurement in physics, we say it collapses the wave function. We reduce it to one state or another. But we got to be careful about the wording we use. So when we aren't careful about the wording we use, we talk about observers. I've seen tons and tons of videos where they say, it's because a conscious observer looked at which slit it was going through. And that is the terminology they use in the Copenhagen interpretation of quantum mechanics. But that is it's misleading to the people who really want to just do this kind of pseudoscience, quantum woo sort of stuff, like Deepak Chopra, who advertises quantum healing or consciousness and quantum physics. We end up with all of this kind of weird stuff, especially in this area. I've walked into bookstores in Ashland and seen an entire shelf just dedicated to the quantum reality of consciousness and things like that. And it's very confusing because to the general public, because they think that this is part of the science. This is not part of the science. This is someone's weird interpretation of that observer effect. The observer effect is an interaction with the equipment. It's not about your consciousness interacting with the fundamental fabric of reality. Deepak Chopra, his Twitter account, he'll say things like, the universe is made of a divine substance called consciousness. But thankfully, we have physicists out there say, no, it's made of quarks and leptons. I love one of his quotes. He says, one should challenge Deepak Chopra first to solve the Schrodinger's equation for a spherically symmetric potential, then talk about quantum healing. I don't know if you've ever seen this slide, this picture before, but I actually kind of feel like this is gives people a pretty good sense of kind of how quantum behavior works. We all reach back behind our computers to plug in a USB, and it doesn't go in. And then we flip it around, we gotta plug it in, it doesn't go in. And we look at it, make sure that we see which way it's oriented, and then it magically works after that. And I love that, because that really is kind of how a lot of quantum mechanics feels. It's like the system behaves as if it's in both states, and then once we make our measurement, it then becomes one of them. So one of the other things I want to talk about in terms of misconceptions is the concept of entanglement. When we have two quantum particles, let's say two electrons, and we want to entangle their states, or we can actually perform an action on them that causes the probability of them being measured in a certain way to become correlated. And the current description in terms of physics is that they're somehow communicating this information instantaneously faster than the speed of light. Keep in mind that is just our model of how we're describing the behavior. Just like, we describe gravity as a force, and then Einstein comes along and describes it as like space-time and bending in space-time. There's always other models that are going to come along and describe the behavior differently. And right now, the model that we use for describing this is that they communicate back and forth, and that's because of something we call Bell's inequality that led us to believe that statement. I would be hesitant to actually believe that there is some sort of faster than light communication, but I'm not a physicist. I'm not going to get too deep into that right now. But as far as quantum computing is concerned, assume that this entanglement is happening, but there's no way to get information to transfer faster than that, or faster than the speed of light. If you're familiar with Einstein's special relativity, you would see that if you could transfer information faster than the speed of light, you would essentially break the fundamental axiom of causation in the universe, and then we have all sorts of problems. So I have a feeling we're not going to see faster than light communication out of something like this. So think of this as just a tool for correlating two states, not as a means of transmitting information faster than the speed of light. Another one that is lovely to see in the news is quantum teleportation. I see stuff like this all the time. Every time the Air Force works on one of their one of their satellites, or China does, we see tons and tons of articles saying, beam me up, Scotty, scientists teleported photons 300 miles into space. They keep talking about how we're teleporting particles. And, I love this XKCD comic that actually points out that it's like, the media kind of reports on this wrong. Because the fact is it's a very different thing than what the media is claiming it is. Quantum teleportation, I really wish someone had picked a different name for it, honestly, because the idea is that let's say you have a quantum state. You have a particle in a state in one place, and you want to transmit that state to another location. What you can do is by sharing, you can entangle your couple qubits ahead of time, share those, and then perform a measurement on your state, and then send it over like a classical channel, like a radio wave or an Ethernet cable. Send it at the speed of light through normal data, and then at the other end, using that data and your pre-shared entangled bits, you can then recreate this same quantum state that you put in. That's what quantum teleportation is. I really don't like the name of it because the general public thinks that it's something that it isn't. So now that we cleared up a few of the misconceptions, what are quantum computers good for? Here's Richard Feynman. He's really considered one of the fathers of quantum computing because he's the one who really said that if we want to simulate these chemical reactions, chemistry, things at a subatomic level, we're going to do a lot better at it if we're using quantum information instead of classical ones and zeros. If we can represent the system in terms of superpositions and entanglement, we will have a lot more success actually simulating our natural world, because that is what nature is made of, is quantum states. So in a conventional computer, we'll have high and low voltages, zeros and ones. And when we actually want to perform a procedure on our data, we have ones and zeros in RAM, and we want to do something with that, what we end up doing is we take our ones and zeros, we apply a procedure to it, and then finally get our answer. And this is, we're applying it on one state. Now, what's exciting with quantum computing is that we can essentially create lots of states simultaneously. So, while this, what is this, a 16-bit register or something? If we created the, same number of 16 logical qubits that we could store quantum, superpositions in, we could essentially create a superposition of all of the states that we wanted to analyze. And so let's say we wanted to run this for, thousands and thousands of different starting points. We could just load all of those starting points into our quantum RAM or quantum registers and then just do them all at once. And if we phrase our algorithm in such a way that there's only one correct answer, it takes I'm not going to lie to you, it does take a lot of clever reconfiguration of your algorithm, a lot of math to really understand how to phrase a problem like this. But the idea is that you can create a lot of algorithms, or you can port a lot of algorithms over to this sort of problem and get a quantum speed up. You can, for people who aren't familiar with quantum information, you can kind of think of it as a form of parallel processing, a very specific kind. It's really, really useful for certain problems. I don't know if anybody here, Josh told me not to put this in, but if anybody has ever studied complexity theory, I just wanted to point out that the bounded quantum polynomial space encompasses all of polynomial, but also includes non-deterministic polynomial. So I just figured if there was any engineers here, that's good to know. But I'm going to skip that. If you want to know more about that, talk to me later. So in quantum computing, we have a whole set of milestones that we're trying to get to, or that we're trying to accomplish in order to keep the field progressing. So earlier on, we really needed to just show that there was a theoretical advantage to quantum computing. And that was, there was some early papers on this. This really got traction when we applied the feasibility, when we actually started talking about real world problems in terms of like theoretical speedups, and one of them was Shor's algorithm. I think that one got a lot of publicity because it demonstrated that you can actually solve this problem of factoring prime numbers that was intractable before. So then we had to go on to the point where we could actually have programmable quantum gates. So when we actually applied some of this, we saw an application system through like the D-Wave computer with an adiabatic quantum annealer. When we got to programmable quantum gates, which is kind of like the universal Turing machine of quantum, we started actually having some of that with like the IBM computer and some of these other superconducting qubit systems and trapped ion systems. So then one of the next milestones we really needed to get to was we needed to prove quantum supremacy for some sort of contrived problem. We needed to find some sort of problem that we said, yes, this works better on a quantum computer. And right now, a majority of the industry, of the field, is getting behind Google right now in claiming that 2 months ago they actually accomplished this. That we have actually achieved a quantum speedup for a contrived problem. It's not a useful problem, so that's kind of the next stage of the industry. We need to find algorithms, we need to find problems that actually mean something to somebody and just show that, yeah, we're doing this a lot faster on a quantum computer than we ever could on a classical computer. That's where we're at in the industry. After we get that, we need to increase the quality in which we can store the qubits, and we also need to increase we need to lower the error rates when we apply these gates to them. So just like in a classical computer, you have like ands and ors and this stuff, but in quantum we have similar gates. But the problem is there's a certain percentage of the time that they fail. That you lose coherence of your qubit, and so we need to start getting those error rates down, and that's really what the physicists are working on. They're trying to get those error rates as low as possible so we can actually use their systems. So as software engineers, like me, we're interested in creating, finding the problems that we can run on the hardware that we do have. Physicists are really working on trying to make the hardware better. So once we get better hardware, we're going to move on to a stage where we can actually start introducing quantum error correction, quantum fault tolerance. Because if we can describe a logical qubit that uses a whole bunch of underlying qubits, like you do error correcting codes in classical computers, we have error correcting codes in quantum computers. A basic one would take about 7 qubits to create one logical qubit. But the more qubits you add, theoretically you could deal with there's an error bound that we're trying to cross. And so we really need to get to the stage where we actually are creating logical qubits that have lower errors than the underlying individual physical qubits. Because if we can get to there, then scaling it out is a lot easier. But we really got to get the hardware down under that error bound so we can build our logical qubits. And then once we do that, then it's about scaling out the architecture with full fault tolerance. If we can actually have an architecture where we know, yes, when I perform this operation, that operation is what happens. And there may be a whole bunch of underlying hardware that goes into that, but as a developer, I want to know that this gate does this thing. And then that is going to change the type of algorithms we can run. Things like Shor's algorithm, things like there's other algorithms that are really game-changing, like Grover's search, that is going to make searching through data sets a lot faster. But those are all those types of problems can only really run on full-scale fault-tolerant architecture. So we got to get to there in order to run those. But there are potentially useful problems that we can solve in the meantime. So the slides are going to get blurry at this point because these are actually pictures I took from the audience when I was at the Q2B conference. They talk about, I just kind of cherry picked a few that I thought you guys might be interested in. They talk about some of the important milestones that we need to, or that we can deal with. And on the near-term quantum, so like I just said, once we get our first logical qubit that has an error less than a physical qubit, that's the revolutionary era. That's when things are totally game-changing. And so there's a whole bunch of problems, both in physics and industry, that we can probably solve with that we just can't even imagine doing right now. But in the meantime, there are actually problems like options pricing for finance, like Ford was working on a vehicle routing system that seems to have promise, and a lot of there are some basic chemistry problems that we can actually solve on one of these noisy computers. John Preskill was the one, I believe, who coined the term NISQ, which is the noisy intermediate size quantum. So this is going to be the class of process. This is what we're kind of entering into now. We have these processors that essentially, they don't have fault tolerance like the ones of our dreams, but there are problems that we can solve on these. And some of these groups, some of these analysts tried to break it down into time frames in terms of what sort of problems can we solve. And this one in particular was talking about materials design. So these are chemistry simulation problems that might be able to be solved with each stage. With the stuff we have now, we're looking into, active sites of simple catalysts, functional groups of small molecules. As we get more and more, we'll start looking into more industrial chemicals. But then once we get into fault tolerance, we can get into like synthetic enzymes and protein design and that sort of stuff. But because those are pretty large molecules, thousands of amino acids potentially that we have to deal with, we're really going to need full fault tolerance for those. But in the meantime, there is problems that we think we can solve with these other ones. Here's another one that I thought was pretty interesting is they talk about different industries and the types of problems that they might be able to deal with in each of these stages. And then also the total industry impact, so the operational income. And I found this interesting. They think that within the next few years that this is going to be a $2 to $5 billion industry. But as we get more broad quantum advantage, a decade from now, it's going to jump up. They think about 25 to 50, and then after fault tolerance, some people think it's $1 trillion. Like, who knows how big it gets after that, right? Because if we can start simulating chemistry on proteins, Humira, for instance, at AbbVie, is one of the most profitable drugs of all time, and it's a designer protein. If we can start computing those to solve more problems than rheumatoid arthritis and psoriasis, like we're talking a lot of money, and there's going to be a huge demand for this. When I was at this event, I saw data scientists from every pharmaceutical company there, like GlaxoSmithKline, AbbVie. There's a lot of people there from the pharmaceutical industry because they see the value in this. And also finance, the banks, they want to do options trading, get into the high frequency trading space. If we can do computational fluid dynamics, we can simulate all sorts of stuff. Wind tunnels, Airbus is investigating things, BMW is investigating stuff. There's a lot of action going on right now that people are investigating what they can do with this stuff. Here's just one of they were talking about a specific algorithm. I won't get into VQE, but some of these algorithms, we call them heuristic algorithms because they aren't these nice, pretty fault-tolerant algorithms like Grover's and Shor's, but they do offer a lot of promise in terms of potential speed-ups, and so this is why a lot of people are exploring this heuristic algorithm space. I love this picture a lot. So when these hardware vendors, or IBM and Google and all these guys, when they fire up their machines, there's so many calibrations that have to happen in order to tune the error tolerance, to try to get that error tolerance as low as possible. And I love this. They highlighted a lot of the stages and color coded them and pointed out that like these two right here represent one person's PhD thesis. Like somebody spent years just working on this little piece. Like that's how much work is going into these projects. And this is just a calibration sequence for 2 qubits. So while they're increasing, they're working on getting that error rate down for us to run our hardware on, or our software on, there's actually a lot of advances going on in terms of making the algorithms more efficient too. So like we just look at in the last, decade even, like here's a error correction cost for performing a certain chemistry problem, I believe. And we were looking at algorithms that were going to take 10 to the 18 gates, and like that's a lot of operations in order to really make this actually work. And so we're thinking, oh yeah, this is way off. But like just in the last decade, just with the algorithm, just people tweaking these algorithms and stuff, we're down to 10 to the 7th. Like this is massive. Like, meanwhile the hardware is getting better and better, and the algorithms are getting more and more precise. We're closing this gap from both ends. That's what's exciting. And what I included this picture because every time I talk to somebody about quantum computation, they always ask, what does a quantum algorithm look like? Like, what would a real world quantum algorithm even look like? This is actually JP Morgan and Chase was showing this slide, and they were just I just like this one because this shows one of the early types of algorithms that we will probably see running on a quantum computer that's actually doing something useful. And the idea is that they're actually trying to forecast an option. They're doing Monte Carlo simulation, and it's pretty cool, but it's going to take too long to describe what's going on here. And but I just wanted to demonstrate, just show you that like that people are actually coming up with stuff. Like this is actually, coming along. So I kind of wanted to end things. This is a slide David sent me. That the fact is that as we're getting closer and closer to fault tolerance, the demand for the software engineers that can do this is just growing, is going to just explode. And in the previous, like the classical computing era, as we developed our computers, and companies like Apple and Microsoft were competing to provide software for these new machines, we were in an era where there was, this was after World War II, and then the Cold War was going on, and there was a lot of money getting poured into Silicon Valley. And also Stanford was right there. They saw the potential, and they built programs to provide the engineers to fill these new occupations that were emerging. The thing I worry about with this industry right now is that the barrier to entry into quantum computing is high. You have to have a very strong mathematics background. You have to have understanding of quantum physics, and you have to be a software developer. Like, this is not a hobbyist sport. Like this, before the guys who were building radios were the ones building processors. And a lot of them were hobbyists. And I feel like in order to fill these software positions that are going to be emerging in the next decade or two, where are they going to come from? And because they got to already have a STEM background. And this is what terrifies me, is that our pool is really small compared to China, who is also investing just as much into quantum computing, and they're siloing a lot of the results. Like, we really don't know a lot of what's going on over there. And if we both develop quantum computers at roughly the same time, they are going to have a much larger pool of STEM graduates to train in quantum computing than we ever will. And so, so my hope is that, anywhere we can, encourage, individuals and governments and education organizations and stuff to all really push for STEM to prepare people for this industry, because we're going to need thousands and thousands of developers, and they're not going to exist. So I hope that inspires some people to go learn some math and maybe start experimenting with getting into the quantum computing space. So that's it. So any questions?
Yeah, I had a question that, like, the exact skill sets and stuff like that are needed.
Yeah, so that's a very good question. So for instance, I started studying quantum information when I was in my 4th year of college, and I had a pretty strong background in both mathematics and computer science. And I will tell you that it was still a difficult topic to pick up. Physics, like quantum physics, would have helped a lot if I had been exposed to some of that beforehand. But ultimately, like high-level linear algebra, differential equations helps. I mean, in order to develop a lot of the quantum algorithms use, Fourier analysis, which is high-level calculus, or builds on high-level calculus. So just really strong math background, and it's kind of a hard one to push because you can't force people to be passionate about math, I've found. So I'm not really sure how we approach getting people passionate about math, but we need to. That's a problem that I think needs to be solved in communities all around the country, is how do we get people excited about math and recognize that this is going to be what they're building their future on.
Awesome.
Yeah.
You had mentioned something about the loss of coherence.
Uh-huh.
Does that have anything to do with entanglement of the cloned particles?
Yeah, so a quantum state consists of like a pure quantum state is essentially it's describing the superposition of all the qubits within that state. And you can have entangled bits, you can have non-entangled bits, but ultimately either that state should be in one, you should be able to describe what each of these states look like. And if decoherence is essentially interactions with the environment, it's kind of like if you think of a bit in a computer, like a classical computer, it's kind of the equivalent of just having a bit flip. Just sometimes you'll have a high voltage and it drops and you get a low voltage, or you have a high magnetic potential and it becomes a low one. And so that's, there's more things that can flip in a quantum state. So in a classical computer, a 1 can become a 0 can become a 1. In a quantum computer, you can have phase flipping and you can have the actual bit flip as well, and you can have combinations of the two. So there's more types of failures that can happen to a quantum state than would happen in a classical system.
Is a quantum state, is that what is being referred to with terms like negative spin and charm versus strange?
So those are the types of quarks: up, down, strange, charm,
right,
top, bottom.
Yeah.
Those are different types of quarks, but each of those have spin properties, like whether they're half spin or whatever, and that's what classifies them as different subatomic particles. I'm not a physicist, but I'm kind of speaking for them right now. But ultimately, it's the properties of those particles that we're describing in terms of quantum states. So like I mentioned, polarization of light. Light can be vertically polarized or horizontally polarized, and you can experiment with that with just polarization film, and that is a that is a property of the photons that are traveling through the medium. And things like, there's a lot of properties that can get entangled into those, like position and all sorts of stuff. And you can actually get macro objects that that can actually kind of have these quantum states. But ultimately, in terms of information from the programmer's perspective, we don't really care what it is underneath. Just like as a programmer, I don't care if my 1 is represented as a magnetic domain or if it's represented as a voltage. It's a 1 or a 0 to me. I'm a programmer. Logical abstraction. Cut out all of that physics stuff, and let's talk about logical abstractions. So a quantum state is actually, when we're talking quantum information, we're talking about the logical abstraction of the superpositions of ones and zeros. But the underlying implementation can be a whole host of different types of things that I am not really qualified to talk about. It can be photonics, it could be trapped ions, it could be superconducting qubits, it could be...
Okay, so that's where the hardware
Yeah.
difference comes in.
Yeah, so like for instance, Xanadu up in Toronto, their system actually uses light polarization, while ion Q and these other systems that are using trapped ion, they're using electron spin. So you can actually have different quantum phenomena underlying your system. But from the programmer's perspective, that I'm trying to that I care about more is I don't care what the underlying system is. Just tell me what my error rates are for my gates. Tell me what my error rates are for temporal fidelity, and let me deal with it.
Got it.
I didn't take good notes, but there were certain slides that
Is there one that
had questions. I don't remember.
I can back up? Say when.
And go the other way. It's not there.
Here?
Yeah.
Okay, I just wrote this list today. This is kind of my definition of what I think. This is how I classify the milestones. They kind of overlap quite a bit with the other presentations milestone list.
Yeah. Can you further describe the difference between logical qubits and
Yeah.
physical qubits?
Yeah, so for instance,
You were just saying.
yeah, like in if we have, let's talk about this in terms of a classical computer. So in a classical computer, you can actually have a physical bit, which would be the voltage or whatever. And there, in memory, you may have that, 1 or 0 in there. But if you're worried about the fidelity of that, like is it going to change? You can introduce a couple extra bits to kind of represent, so that way, like let's say you have 3 bits or whatever. If if one of them changes, you can determine if the other, like you can kind of guess like, oh yeah, or 4, I think 4 bits is what a Hamming code operates on. Yeah, so anyway, if you have these bits that you can basically reconstruct like...
Sort of like a compression type of deal.
It's kind of the opposite of compression. So compression, you're using less bits. This, we're actually using more bits. But we're using more bits to kind of correct things. So it's kind of like, you can... One very simple way to think about it is just duplicate. The simplest form of fault tolerance you can think of is do something twice.
Right.
And if they...
Multiple duplicates. And
Yeah.
Pick the drift.
Or 3 times. Let's say 3 times. Do it 3 times and then vote.
Right.
Like if you do, if a bit, if 2 of them are 1, then that 3 bits represents a 1.
Yeah, the third one's probably.
Yeah, so hopefully they would all 3 be 1, but if one of them gets flipped, it's okay, right?
Probability.
The probability of 2 of them getting flipped is really low.
Reduced, yeah.
So that's probably one of the simplest classical implementations of a logical bit. So basically, you would think of as that bit is those 3 combined bits,
Gotcha.
and that system would have better fidelity than 1 bit by itself.
Gotcha. So how come with qubits it's 7 to 1? Any idea?
I can describe that more afterwards. It has to do with Steam codes and error correction, and
Probably that's
it's basically an extension of the Hamming code to the quantum space, and it's not something that I'm going to be able to describe in
Yeah.
right now.
Yeah, I don't know that I'll capture that much.
Yeah. Is that it?
Yeah.
All right.